Good morning, dear students. Well, we have completed the first chapter, electric charges and field, and I hope all of you have done the homework that I have given. Today, we will discuss the chapter number 2, that is electric potential and capacitance. Before going to start this electric potential and capacitance, one must understand the concept of the conservative force, conservative nature. What do you mean by this conservative nature or conservative force? We say that in the first chapter, Coulomb's law is the force between the two stationary point charges. And already in the first year, we have studied the gravitational law. That is a force between the two masses. Force between the two masses. So the both Coulomb's law and the gravitational law are similar. They are inverse square laws. Only the difference is proportionality constant. We know that a gravitational law, or we say that a gravitational field, is a conservative force. A gravitational force is a conservative force. What do you mean by this conservative force? Conservative force, it is the work done by the body does not depend upon the path followed, but it depends its initial and final position of the body. It is independent of the path followed. Why I am saying that conservative force? Because when we talk about the electric potential, one must understand the conservative nature of the electric field. We talk about the gravitational field in the first year. A gravitational field is a conservative force. Like that, electric field is also conservative in nature. Say that Coulomb's law is inverse square law. A gravitational law is an inverse square law. As I said that earlier, that its difference is only the proportionality constant. If I want to bring a charge in the electric field, I must do some work to bring that charge in the presence of the electric field. No matter what path I have followed, but I have to bring that charge from one point to the other in the electric field. So, first we have to understand the concept of the conservative nature of the electric field. As I say, conservative nature, it does not depend upon the path followed. It depends only on the initial and final positions. Like that, if I want to move any charge from one point to the another point in an electric field, it should not depend upon the path followed, but depends only on the initial and final positions. That is the conservative nature of the electric field. Right. So what I can say that conservative nature of the electric field. I write here that is conservative nature of electric field. So this conservative nature of electric field means work done to move a charge in an electric field is independent of its path followed, but depends on its initial and final positions. final position of the charges. So this is the conservative nature of the electric field. We say that work done to move a charge in an electric field is independent of its path followed, but it depends on its initial and final positions. No matter what path is followed, but it should be depends on its initial and final positions. That is what the conservative nature of the electric field. Usually in the examination they ask for one marks that what is the meaning of this conservative nature of the electric field. Then using the concept of this conservative nature of the electric field, we will define the electric potential. Say that to define the electric potential, once again I will recall the first year chapter number 8, gravitation. In that gravitation we talk about the potential energy. Potential energy is what? Potential energy, it is the energy possessed by the body by virtue of its position or configuration. Right? So gravitational, when we place any body in the presence of the gravitational field, it must have some potential energy. Like that, any charge is present in the presence of the electric field, it also has some potential energy. That is why we define that electric potential. So, to define electric potential, I say that electric potential has to define here by using the concept of the conservative nature of the electric field. By using the concept of the conservative nature of the electric field, we will define electric potential. So, electric potential is the work done to move a charge. This is the work done to move a charge or carrying a charge, a unique positive charge, from infinity to that point, against the electrostatic field, or electrostatic force. I will repeat once again. Electric potential is the work done. It is the work done in moving a unit positive charge. From infinity to that point against the electrostatic field. So how we can say that? How we can understand this definition of this electric potential? Say here, there is a charge. There is one charge, and we know that every stationary charge produces its own electric field. It has its own electric field, like this. It has its own electric field. If I want to bring a unit positive charge from infinity, what do you mean by this infinity now? Infinity means where the electric field ends. It's the point where there is no electric field, where there is zero electric field. We can say that there is a infinity point. Now I can say that in this region, I say that there must be the electric field. If I come outside from this region, I will experience does not experience any force. It does not experience any force here. So if I don't experience any force, then I can say that this point should be the infinity point, because there is no electric field, and comparatively this unit positive charge is very small. So it does not alter the configuration of this electric field. That is why we call this the infinity point. So if I want to bring a unit positive charge from infinity to this point, I will call it as a reference point A. If I want to bring this unit positive charge from infinity to this point, that work done is nothing but the electric potential. So we define that work done to move a charge from infinity to that point against the electrostatic field is nothing but what? My electric potential. No matter what path I have followed, I can bring this unit positive charge directly to here, or I can bring this unit positive charge from this point to here. I can bring this. No matter whatever the path follow, but it depends on its initial and final positions. I can come from this angle, this path. I can follow this path. Alright? So I can follow this path also. At any point. Say, if I want to bring this unit positive charge from infinity to this point, no matter what I have followed the path, but it depends only on its initial and final positions. And bring it. That is nothing but the electric potential. So we write that work done to move a unit positive charge from infinity to that point against the electric field. Against the electric field is nothing but what? Electric potential. I write the definition here. Written here. Work done to move a unit positive charge from infinity to that point against the electric field or electrostatic force is nothing but the electric potential. Why I am saying that we are doing the work against the electrostatic force? Because there is a unit positive charge, there is a positive test charge, and positive test charge, the electric field is always away from this charge, like this. So if I want to bring this unit positive charge from this point to this point, from infinity to this point, I have to do the work against this electric field. I have to do the work against this electric field. That is why I written that is work done to move a charge from infinity to that point against this electrostatic field or electrostatic force. We call it as the electric potential. Right? So electric potential is denoted by symbol capital V. V is equal to W divided by Q. V is equal to W divided by Q. What is W here? W is the work done to move the unit positive test charge. Unit positive test charge. From where? From infinity to that point. Which point? I have bring that point from infinity to A. So infinity to A. So this V is equal to W infinity A upon Q is nothing but the electric potential. Electric potential. So we say that V is nothing but the electric potential. Now SI unit of electric potential is volt. SI unit of electric potential is volt. When you can say that it is electric potential is 1 volt if W is equal to 1 joule and Q is equal to 1 coulomb. If W is equal to 1 joule and Q is equal to 1 coulomb, then V is equal to 1 volt. Then V is equal to 1 volt. That is V is equal to 1 joule divided by 1 coulomb is equal to the 1 volt. This is one of the electric potential, right? We will also define the volt. If 1 joule of work is done, if 1 joule of work is done in moving a charge of 1 coulomb from infinity to that point against the electrostatic field is called the 1 volt. It's called the 1 volt. So today we have discussed the conservative nature of the electric field and electric potential. Right? Electric potential is the work done to move a unit positive charge from one point from infinity to that point against the electrostatic field. Remember, if I want to move or carry a unit positive charge in the electric field from infinity to that point, no matter whatever the path I have followed, I can move this charge from any path. I can move this charge from this way or directly this way or this way in any other way, but it depends only on its initial and final positions. Okay, in the next class we will talk about the electric potential difference.